Okay, we're going to be talking about continuity in this video. Very important concept in calculus. So what is the definition of continuity? Well, here's the technical definition. Function is continuous at a point, C, provided the following conditions are met, is that the point is defined, the limit at that point exists, and those values are the same. The way that I learned it, so let's just say this is like some function like this. And I want to know if this function is continuous. Well, can I trace this function without picking up my pencil? If that's the case, it's continuous. A bit more technical, we got to use these things. You have to memorize these three things, and you have to do these three things when you're specifically asked to find continuity. Okay? Continuity on an interval, same idea here. If you're given the closed interval, closed means that you have the endpoints as well. It's continuous. The entire interval is continuous if it's continuous between the those 2 points, and if it's continuous, it's kind of hard to see here, but as we go to the right of the one endpoint and we go to the left of the other endpoint, if those values do exist, then yeah, we're continuous. Types of discontinuity: removable, also known as a hole. So removable continuity, also a hole. So like, get this function, there we go. That's removable because there's a hole I cannot trace over it. So I can trace my pencil, I need to pick it up and continue it on this side. Jump. Say if I have a function that's defined there, and then it's over there. So same thing, here, and I have to jump to pick it up right there. And infinite is like if you have an asymptote, kind of like that. Okay, so that would be infinite. It has an asymptote. So let's go ahead and determine whether the following function is continuous at x equals 2. So 2 ways to do it. You could graph it and then use that to go through your 3 steps to figure it out, or you could do it algebraically. Same thing, you have to go through the 3 steps algebraically. It's more common to use the algebraic method, so I'm going to go through and solve this algebraically. So step 1 is I'm going to say that how exciting it is. Whoa, okay. This is like balancing for his life. I wasted everyone's time, right? That's why you should get a real webcam and not a phone. All right, very gentle. Okay, so to find this algebraically, we need to say that f of 2 is defined. Well, we can find, in this case, we have h, not f. We can find that. Look at my piecewise function. This is going to be x squared minus 4 over x minus 2 everywhere except for 2. At 2, it's actually 4. So that equals 4. That implies that it's defined. So step 1, it good. Step 2. Step 2 is I have to prove that the limit exists. So I have to say that the limit of this x approaches 2 of h of x. I wrote 2. H of x. Let's just go with it. That's an x. Exists. So let's look at that. So in order to do that, I have to do the limit from the right and the left. I'm going to save you a little bit of time, though. You don't necessarily look at the left or right. Just find the limit in general of this. So let's find the limit as x approaches 2 of this x squared minus 4 over x minus 2. Because you're going to get the same thing if you do it right and left. So for these piecewise functions that are like it's this function everywhere except for here, you can just do the limit at that. So this is just like we did in a previous video. It's in the archives, finding limits algebraically. You can't just plug in a 2. You're going to get 0 over 0. There's a hole, so we're going to have to factor the top. X plus 2, x minus 2. And some magic happens. X minus 2 go away. Left with just x plus 2. So the limit x approaches 2 of just x plus 2. Plug it in. You're going to get 4. Okay, so this exists. Be a lesson out there. Go buy a webcam. Don't use your phone. Because every time there's a notification, it vibrates and whatever. Okay, last part of this example is, well, does the limit and the value, are they the same value? Are they the same height? So let's look at the limit. X approaches 2. H of x. Does that indeed equal h of 2? Well, I just said h of 2 is 4, and I said the limit is 4. So this does work. That works. That works. That works. So awesome. So therefore, h of x is continuous at x equals 2. All right. Find the values for x at which the given function is discontinuous and identify the discontinuity type. So this is kind of important. It needs to be continuous on the interval. Not on the interval, on the domain. What was I thinking? It needs to be continuous on the domain. So for what we're looking for specifically, textbooks are going to have different things about continuity on a domain. I'm just specifically looking at the endpoints of the domain. So from negative infinity to infinity, is from negative 3 to 3, just like that. And then I'm going to look at it's continuous inside of that. Okay, so let's look at this guy right here for the first example. This does have a domain restriction. In case you don't know what it is, it's supposed to be, it's a square root, so it has to be greater than or equal to 0. You can factor this. You're gonna make a little chart. This is negative 3 and that's 3. Going through this kind of quickly, but you should have been able to do this before from pre-calculus. This is negative, it's left of negative 3, it's negative right of 3, it's positive in between. So my domain is right here. So the domain is from negative 3 to 3. So is it continuous inside that domain? There's nothing else weird going on, so yes, this is continuous. Because I'm just looking for discontinuities. I don't need to prove that it's continuous, I just need to find the discontinuities. So there are no discontinuities, so this is continuous over the domain. Again, the textbook we use, the domain, just looking for like the endpoints. This guy right here. Is this continuous? And essentially, I'm looking at the fraction. I'm looking for vertical asymptotes. Those are infinite. I'm looking for holes. So first things first, I'm going to factor because you got to find holes first. So let's factor the top and bottom. We're going to get x plus 3, x minus 3. All over x minus 3, x minus 2. Yep, and if you notice, these are going to cancel out. So I'm going to have a hole at x equals 3. We already canceled out. Set it equal to 0. And then, so now the holes are taken care of. Jump's not going to happen unless we have a piecewise function in there somehow, or absolute value, which is defined by piecewise function. So don't worry about that. Other one is asymptotes. You only have asymptotes vertically speaking if you have, well, certain trig functions, whatever, or if you have a fraction. So look at this fraction right here. You have on the bottom cannot equal 0, so that minus 3 already got canceled out. So I'm going to have a vertical asymptote at x equals 2. So let's get very specific here. Where are my discontinuities? So at 3, you have a removable. I can't spell it. There's no E until the end. Removable. And then at 2, that is infinite. Okie dokie. Last one has a lot of weird functions on it that I'm hoping you remember how to graph. So for the domain, we actually have to check on the domain of each individual term, because this one gets a little wacky, and make sure that the domain is good. And then our overall domain is going to be our overlapping domain. So like for arctan, if you don't remember what that looks like, something called the Google out there. But essentially, I'll just draw it up here. Arctan looks like this. Goes forever to the left, forever to the right, pi over 2 to negative pi over 2. It is continuous everywhere. So for the domain of arctan, for arctan of x is all real numbers. Okay, no worries there. Next part is going to be the ln of x. Again, don't remember how to do that. Look it up on the old Google machine. But the ln of x looks like this. It does have a vertical asymptote, so that's only going to happen when x is greater than 0. And then that's it for each individual piece, because the bottom piece is a polynomial. So essentially, I'm just looking for when x is greater than 0. Now let's look at this for discontinuities. So can't have the bottom equal to 0. So when is the bottom equal to 0? Well, we'll have a vertical asymptote x equals plus and minus 2. Kind of. Not really. But not really. Anybody know why it's not really at plus and minus 2? Because negative 2 is not in the domain. So we only have the positive 2, not the negative. Okay, so if you have a pencil, you would just erase it. I don't, because you can't see pencil on my recordings. So we only have x equals 2, and that is going to be infinite. These are my discontinuities. All right, and that wraps up finding continuities up there, discontinuities down there, and that wraps it up.